All right, welcome back to 7.3. We are going to be solving some exponential function or exponential equations today. Before we get to that, again, we are going to quickly review what we did last time. We were actually transforming the functions for the graph. Okay, so we're going to look at this warm-up question. It says, given the function y equals to k to the power of x, write the equation of the image graph after the following transformations. It says it's been vertically stretched by a factor of 5. So this means a is equal to 5. It's horizontally compressed by a factor of 0.25. This means b is 1 divided by 0.25, which is 4. Translated 2 units vertically, so this is d equals to 2. And reflected in the x-axis, that means x-axis is the horizontal one, so y changed, therefore a is less than 0. So your final answer would be y equals a, which is 5, but because a is negative, so negative 5 times k to the power of b, which is 4. There's no value of c, so it's simply 4 to the power of k to the power of 4x, and then move 2 units up, so plus 2 at the end. Okay, so that's what we did last time, right? Remember, usually there's a value of c as well, which is horizontal movement. Okay, but not in this question right here. Okay, so that's what we did last time. Today, again, we are going to move on to exponential equation. So here it says an exponential equation, exponential equation contains a power with variable and the exponent. Okay, so again, the variable is the exponent, and if it's an equation, then we call that an exponential equation. Okay, we've seen some of these equations in the past, and we didn't know how to solve it. We're gonna show you one particular type today. It doesn't work. The method I'm going to show you today does not work for all the exponential equations, but I think this is a good start. Okay, so let's see. It says 3 to the power of x is equal to 1 over 243. So what we're going to do is, as long as we have the same base, okay, as long as we have the same base, that means that the two sides of the equation will be equal if the exponents are the same. So the key here is to make the base the same, because again, once the base are equal, then that means as long as the exponents are equal, then they will be equal to each other. Like for example, 3 to the power of 2 is equal to 3 to the power of x. Well, this is easy to do because you can see it's already base 3 for both sides. That means x would have to equal to 2, right? Because the base are the same, therefore if the exponents are the same, then they will be the same. So that's the idea. Okay, so what we're going to do is we're going to turn this into base 3. Now 243, we can write that as a power. 243 is the same thing as 3 to the power of 5. Okay, that's what it is. And then this is still not base 3 yet. Well, it is base 3 in the denominator, but this is a fraction. This is not a fraction on the left. So if you recall, this is the same thing as 3 to the power of negative 5, right? If you have a negative exponent, really what you do is you kind of write it in the reciprocal form, which is 1 over 3 to the power of 5 here. Now, once you have this, then you know x would have to equal to negative 5, and you're finished. Okay, so that's the first example. For part B, you do the same thing. Okay, so here you have 2, and that's 16. So we need to change to the same base. Now, we can't really change 2 to base 16. Okay, well, technically you could, but then it's much more difficult. So rather, what we do is we change 16 to base 2. Recall 16 is the same thing as 2 to the power of 4, right? That's 16. And the exponent remains the same as x plus 3. Okay, so now you can see we have base 2 for both sides. Now this is 2 to the power of 4. We have a power here, we have exponent there, and we have exponents here. Recall from math 10, or math 9 actually, if you have exponents back to back, really that means you're multiplying the exponents together. Okay, so you have 2 to the power 4 times x is 4x. Be careful, here's the common mistake. It's 4 times 3 as well, right? So it's 12, not just 3. Okay, so it's 4 times x and 4 times 3. So now you can see we have the same base. Now once you have the same base, that means as long as the exponents are equal to each other, then these two sides of the equation would equal to each other. So what you need to do is you set the exponents equal to each other and then solve for x. So I can solve for x by minus 4x on both sides. That's negative 3x equals to 12. Divide both sides by negative 3, you get negative 4. And there is your answer. Okay, so the key is to make the base the same. And once you have the same base, then you can make the exponents the same and solve the equation right there. Okay, so there are 2 questions here for you to try. Good luck. Okay, I'm assuming you finished it. Again, you need to change to the same base. Now, you cannot make 27 to base 9. Again, you could, but it's slightly more challenging. And you can't really make 9 as base 27 either. However, we can change 27 and 9 to base 3. Right? We can actually change both sides this time. 27, recall, is 3 cubed. 9 is 3 squared. Okay, now you can see both sides of the equations would have base 3 now. So these are the exponents back to back, so really just multiply them together. That's 3x. On the right hand side, 2 times 2x minus 1 is 4x minus 2. Again, be careful, not just minus 1. You can solve for x, minus 4x on both sides. You get negative x equals negative 2 divided by negative 1. Oops, x equals to 2. Okay, hopefully that's what you got. Part B, same thing. You could change to base 2, or you could just change to base 8. Either way will work. This is as a fraction, right? This is written as a fraction form, so we can change this to 8 to the power of negative x. Okay, so remember these two are the same thing. 64 is same thing as 8 squared, x to the power of x plus 1. Now, again, once you have the same base, all you need to do is you need to say that as long as the exponents are equal to each other, then they would be equal to each other. Okay, so now we have this linear equation, minus 2x on both sides. Divide both sides by negative 3, you get negative 2 out of 3 for your answer. Okay, hopefully that's what you got for both of these answers. You can definitely verify your solution by plugging the x values, the one you solved, back to the original equation and see they are equal to each other or not, right? So you can always check. All right. So those are the basic examples using the simple exponential or power rules, the exponent laws, sorry. Now we're gonna see some questions with radicals. Okay, see if you remember how you deal with radicals. Because remember, you can convert you can convert from power form to radical form, or vice versa, from radical to power. I'm just gonna do a quick review. 3 to the power of 2, fourth root of that. Remember, not fourth root, that's actually changed to fifth root. Recall, this is the same thing as 3 to the power of 2 over 5. Okay, they are the same thing. Okay, and we're going to use this fact to do these questions. And really, this is the same thing as the fifth root of 3 squared, right? These three are all the same. Okay, so we're going to use this fact to do the following questions here. 3 to the power of x is simply 3 to the power of x. 9, we can rewrite that as 3 squared. Again, you have to have the same base. And then root 3 can be written as 3 to the power of 1/2. Okay, hopefully you remember that. Square root just means the exponent is 1/2. Now we have the same base, 3. This is power multiplying each other. So remember, if you have power multiplied together, you just need to add exponents. So this is 2 plus 1/2. Now you can see x would then just equal to 2 plus 1/2, which is 2.5. Okay. For the second example, similar. Okay, so this needs to be rewritten as a base 2. This would be 2 to the power of 3 over 2. This is 4. Okay, we need to change that to base 2 first. So this would be the sixth root of 2 squared to the power of x. Okay, so this then can be written as a power. So this is 2 to the power 2 over 6 to the power of x. So then 3 over 2, that just takes, what happened there? So 3 over 2 would equal to, now again, that's exponents back to back, so now you can multiply them. That's 2 over 6, which we can reduce to 1 over 3. Okay, so that's what I'm going to do, 1 over 3, x. You can solve for x by multiplying both sides by 3. So you should get 3 over 2 times 3, which is 9 over 2. And that is your answer. Right? If you multiply this by 3, 1/3 times 3 is gone. That just cancels out. Okay. All right. Hopefully that's not too difficult for you to understand. Here are 2 questions for you to try. Okay, good luck. Okay, hopefully you're finished. I will show you this. This would be 2 to the power of, 1 over 3. So x would equal to 3 plus 1 over 3, which is, you can leave it as 3 1/3, that's fine. 10 over 3, 3.3 repeating, all the same thing, okay? Second example, 3 to the power of 2 over 5 equals 27, can be written as 3 cubed. So this really is the same thing as cube root of 3 cubed to the power of x minus 1. Now remember, this is cube and that's cube root, so they just cancel each other out actually. So this is 3 to the power of 5 over 2 equals 3 to the power of x minus 1. So 2 over 5 equals x minus 1 plus 1 on both sides, you get 1 and 2/5. Okay? Hopefully they are not too difficult. Okay, we are going to move on. Okay, so that's this exponential equation part. Now, notice the key to our method is that we need to change to the same base. However, that's not always going to work, right? What if the base are not power of one another, right? What if we can't change to the same base? Well, then what do we do? Well, we're screwed for now, but we will learn a different method later on in this unit, okay? But for now, everything is going to be fine. You know, we can change to the same base. Later on, we'll deal with some questions that we cannot change to the same base, and we'll have a different method. Okay, but for now, everything will be okay. Will be nice and solvable, okay, to using our method right now. Okay, so I want to move on to the next part, which is the application of exponential functions. And we see applications really in the banking, right? Money, because ideally you want your money to grow exponentially, right? Not linearly, because it grows much faster. Okay, here it says when money is invested in savings account, it earns interest. If the interest is reinvested in the account, it also earns interest. This is what we call the compound interest. Okay, so you earn interest on your interest. So you're making the money is doing work for you, basically. Okay, and we call that compound interest. So here's the general formula for compound interest. A principal of $8 okay, is invested in an annual interest rate of I, okay, that's the interest rate annually, with n compounding periods per year. The amount, $8, so that's the amount that you get at the end, after t years is given by, here's the formula, A equals A naught times 1 plus I over n, in brackets, to the power of nt. Okay, so again, that's the initial amount, that's the interest rate in decimal, okay, so this as a decimal, not a percentage, okay, as a decimal. N is the number of compounding periods per year, and I'll show you what that means in a second. T is simply the time in years, okay, in years. Okay, so let's see. Here is as considering compound interest. Suppose you have $1,000 and you want to invest it for a year. Fill in the table according to the information given. So we are just going to take this formula and these information and plug in to the formula. Okay, so we have initial amount of $1,000 and we're invested it for a year. So annually, and with the annual interest rate of 2%, the amount that you get at the end, A, would equal to 1,000 times 1 plus the interest rate is 2%, so as a decimal it's 0.02, divided by n, again that's the number of compounding period per year, is as annually, so it only compounded once a year, to the power of n is 1 times the number of years, which is also 1. Okay, I'm just going to write the expression. Okay, I'm not actually going to calculate for now. Semi-annually will be similar. A equals 1,000, 1 plus the interest rate is 0.02 divided by, now because it's semi-annually, it means we calculate interest twice a year. Okay, so n is now 2. So n times t, 2 times 1. Quarterly, so again, similarly, you plug in the same numbers, except the value of n is going to be different. Because it's quarterly, so it means we count the interest 4 times a year. So now n is 4. 4 times 1. Monthly, you know what that means, right? It means you count interest every month. So that means we have 12 months, therefore n is 12. 12 times 1. It could also be bi-weekly, it could also be weekly, it could also be daily, okay? So there are different compounding periods. You can fill in the table for the rest. It will be exactly the same thing, except now the percentage is going to be a little bit different, okay? So I'll let you finish filling the table. Okay, so here's the table. If you actually filled it in yourself, I'm sure you'll remember this formula for good. I mean, it did it 12 times. That's a lot, okay? Now, notice I didn't calculate because I really want you to answer this question without getting an answer here. It says, which of the above options would give you the most interest and how much would it be? Well, obviously, I think this row will give you the most because it's 12%, that's the highest. The question is, I guess, would annual interest if you compound annually, would that be better, or is it better to compound semi-annually, quarterly, or monthly? Well, it turns out the more often that you count interest, the better it is. And of course, it makes sense because once you get the interest, right, for that month, then that interest for that month will actually earn interest for the next month amount, right? So even though the difference might not be huge, but it does make a difference, okay? It does make a difference. So this one would be the most amount that you'll get, okay? Because it's most frequent and has the highest interest rate. So you can put this into a calculator and get your answer. Let me see, where's my calculator? Okay, so it turns out the amount will actually end up to be $1,126.83 for this one right here, 12% at compounded monthly. If you do it this one, okay, if you chose this one instead, this only gives you $1,120. So there is actually $6.83 difference. So it's quite a bit. I mean, $6 is $6, right? It's good for I don't know, for a fancy Starbucks coffee, right? All right, so there is the formula that we're going to be using for the next bit. Here it says a function that models exponential growth has the form of f of x equals to a times k to the power of bx. Actually, it's not just the exponential growth. It could be a decay as well. Exponential growth or decay. So k would be the growth factor if k to the power of b is greater than 1. But if k to the power of b is between 0 and 1, this would be the decay factor. And we saw this last section, right? But last section we only look at k to the power of x. But this time it's k to the power of b. But I mean, k to the power of b is just a value, which, I mean, similar to what k is, right? So I think last time we said if k was bigger than 1, then it's going to be exponential growth. If k is between 0 and 1, then it's going to be an exponential decay. So just like what we have here. But again, instead of just k, we have k to the power of b this time. Okay, but similar. Okay, so we are going to look at some examples. Okay, and let's see. It says a principal of $2,000 is invested at 5% annual interest rate, compounded semi-annually. How many years does it take to double the amount of money that you have? Okay, so we need to actually set up the equation first. Recall our equation was a equals a naught times 1 plus I over n to the power of nt. The principal is $2,000. 1 plus the interest rate is as it's 5% annually, so 0.05. It is compounded semi-annually, so twice a year. And it says how many years, so we don't know the number of years, so t is the variable, but we do know n is 2. we want to figure out how long it takes to double the amount. So therefore, the end result should be $4,000. So this is the equation. Now we can simplify this a little bit. I will say that I can divide both sides by 1,000. This is a nice number because you just end up with a 2. This is 1 plus 0.5 divided by 2, which is 0.025. So plus 1, it's 1.025 to the power of 2t. Okay, now again, this is an exponential equation that we cannot solve just yet because we cannot change them to the same base. So what we need to do is we need to use decimals, okay? Okay, so here is the decimals web app. So you just need to type in the equation that we have here. So it's 1.025 to the power of 2t. So we just go y equals, in bracket, 1.025 to the power of 2x. Okay, so that's the graph. And then we want this to equal to 2. So you want y equals 2 as your second function. And now all you need to do is to find the point of intersection, which is right here. And you can just, again, double click on the graph. It'll show you the x value right there when y equals to 2, or when they intersect at 2. So you can see, in this case, t is equal to 14.036. So approximately 14 years, your amount will double, okay, in about 14 years. So really, in reality, it's going to be 14 years and 6 months, right? Because that's when they pay you the 0.36, even though it's not quite 14.5, but because at 14 years, it's not quite doubled yet. And they don't give you interest until 6 months later. So really, in reality, it'll be 14 years and 6 months. And of course, in 14 years and six months, it's going to be more than double. It'll be a little bit more than double. But if it's just 14 years, it will be less than double. So in this case, I think our answer should say how many years? It'll be 14 years and 6 months. Okay. All right. You can try the next one and then see how you do. Similar. Okay. Okay. So for the next one here, this case I actually wouldn't. I wouldn't divide both sides by 1,500 because it doesn't really give you a nice number. I mean, it's not bad. It's 5 out of 3. So you can type that in decimals. That's not a problem either. But I just leave it as 1,500 and 2,500. So there's my y1. I use this as my y1, and I use this as my y2. And notice when you find the point of intersection, it's at 12.834. So it's because this time it's okay. It says nearest 10th of a year, but I mean, again, it says it's compounded quarterly. So it's either at 12.25, 12.5, 12.75, or 13. Now, 12.83 is more than 75 already, so it's already more than 9 months. Right, 3/4 will be 9 months out of 12. So it's already more than 9 months, which again, you do not get any interest until you hit the 13th year mark. So I would, to be honest, in my opinion, I think your answer should say 13 years. But I mean, it says to the nearest 10th of a year. I guess if you answer 12.8, that would be okay as well. Okay, but I think, personally, I think your answer should say 13 years. That makes more sense. Okay, last one. The function p equals 101.3 times 0.88 to the power of h models the atmospheric pressure p kilopascals kPa at an altitude of 8 kilometers. If the cabin pressure in an airplane is less than 70 kPa, passengers can suffer altitude sickness. To the nearest kilometer, at what altitude is the atmospheric pressure 70 kPa? Again, what you need to do is, again, simply plug in or on decimals, because again, we can't solve these equations yet because we cannot change them to the same base. You could say that y1, I'll just show you what we do. That y1 is going to be 101. I'll move this to this side now. y1 is 101.3. The base is 0.88, 0.88 to the power of h, so just x. And then y2, we want it to be 70. Okay, there you go. So there's the graph. We now just need to zoom in, double click that point. There you see. At what altitude? It's going to be at 2.89. What's the unit here? I don't think it's meters. 2.89. I'm thinking kilometers. What was it? Does it tell us to the nearest kilometer? So y1 in decimals, this is what you should do. 0.88 h. y2 is going to be 70. The point of intersection, it was 2.891 comma 70. If you want to round to the nearest tenth, it will be 2.9. So you'll be at 2.9 kilometers. Then the pressure would be 70 kPa. Okay, so that's it for this lesson. Again, the key takeaway here is if you're solving exponential equations, that means you need to change to the same base if possible. For now. Later on, I'll show if it's not possible, well, for now, then we can just use the graphing utility, right? Either your graphing calculator, decimals, GeoGebra, whichever platform you prefer. And then, yeah, we can solve the exponential equation. Later on, I'll show you a different method that we can solve exponentials, any exponentials algebraically. Okay, so that's it for today. Let me know if you need help. Otherwise, good luck with your practice questions. See ya.